Alright? Now we want to discuss buffer solution. Previously, we've already solved problems on pH and pOH of acid and bases respectively, for which also we determined the hydrogen ion concentration and hydroxyl ion concentration in each case. Now, there are certain solutions that when you add an acid or a base in small amounts to them, instead of their pH to change, they will be a bit stubborn to changing their pH. You see, you know that if you have an acid, and let's say that the pH is 2, for example, and you add an acid to it again, that is acidic solution, you add another acidic solution into it. Ordinarily, what should happen is to increase the hydrogen ion concentration of that acid whose pH is 2, because it's an acid. And you are still adding another acid into it. What defines this acid is the level of hydrogen ion in it. So we expect that if you have an acid and you add an acid into it, the pH is meant to change. But then, there are some of these solutions that will show a bit resistance. No, I don't want to change my pH. Such solutions are known as buffer solutions, or buffer for short. Here on the board we have the definition that buffer solutions are solutions which are resistant to change in pH when a small amount of acid or base is added to them. So take note of that. Solutions that are resistant towards pH change when you add an acid or a base in small amounts to them. There are 3 types of buffer that we are going to discuss right away. In each case, I'm going to make an analysis of what this buffer solution will contain in excess, what it will contain in large amounts, and what it's going to contain in small amounts. The first of its kind, or type of buffer that I would like us to talk about, is a buffer solution that is made from a weak acid and a salt of that weak acid that is highly ionizable. Please, before I move on into this, I want to state this generally that buffer solutions are usually formed from weak substances. Take note of that. So type 1 of buffer solution we're going to look at is a buffer solution that contains weak acid and its highly ionizable salt. That is type 1. And now, a good example of such is when you have a mixture of ethanoic acid, also known as acetic acid, with its highly ionizable salt like sodium ethanoate, also known as sodium acetate. Now, ethanoic acid, we know from organic chemistry, or acetic acid as we call it, the old name, is a weak acid. A salt formed from it, which is sodium acetate, is highly ionizable. A mixture of these two will give us a buffer solution. Now, this solution, what will it contain in excess? What will it contain in large amount? And what will it contain in small amount? It's very important that we know that. So I'm going to do the analysis of it on the board here, just down here. In each case, I will wipe so that we give room for the next analysis. So let me get my wiper. Alright, so remember we talked about a buffer that contains weak acid and its highly ionizable what? Salt. So let us see what such solution is going to contain. I'm using an example of acetic acid and sodium acetate. So quickly, let me write acetic acid CH3COOH. It is a weak acid, so I'm going to mix it up with CH3COONA, sodium acetate. Okay, now you know that during dissociation, this acetic acid will dissociate and release hydrogen ion. This is positive, this is negative. CH3COO is acetate ion. Acetate ion. Now, this will also dissociate here. Sodium is positive, this is negative. Now, did you take note of something here? That we have the acetate ion here. We also have acetate ion in this salt. Which means that namely, if I am to write a product, we will have excess acetate ion in the solution. Because of course, this and this will give us 2 moles of it. Which means it's in excess in the solution. So what does that tell us? A buffer that is formed from a mixture of a weak acid and its highly ionizable salt will contain excess ion of the acid. Is that okay? I've given an example here using acetic acid and its highly ionizable salt. So in this case, it's going to contain excess acetate ion. Excess acetate ion. Now, what is it going to contain in large amounts? Let's watch what is going to happen. Hydrogen ion from this acetic acid is positive ion. This acetate ion in this sodium acetate is negative ion. Do you know that chances are that they are going to attract in this solution? If this hydrogen ion is released, it can combine with this negative acetate ion from the salt. And once it's combined, it will give us CH3COOH, which of course is ethanoic acid, which of course is also known as acetic acid. It simply tells us that the solution will contain a large amount of acetic acid. So once again, a buffer that contains a weak acid and a salt of that weak acid that is highly ionizable, we expect that the solution will have a large amount of that acid. Because you know, the more this quantity is increased in that solution, the more this quantity is increased in that buffer solution, hydrogen ion will keep being produced, which can combine with this acetate ion from this salt to give us that large amount of acetic acid in the solution. Lastly, what does it contain in small amount? Of course, in this case, it's going to be hydrogen ion. We're not talking about the sodium. We're not talking about the sodium. Is that okay? It doesn't really form part of the buffer at all. It really doesn't. So our interest is hydrogen ion. Hydrogen ion will still exist in that solution, but it's going to be in small amounts. Because of course, like we see, it's only in this species. It's this acid that is producing the hydrogen ion. So it's going to be in small amount. So that's the concept of what this note is about. You can go through that. Buffer solution type 2. This type of buffer solution is one that contains a weak base and its highly ionizable salt. Can we think about any weak base? Of course, we have bases like sodium hydroxide, potassium hydroxide, calcium hydroxide. Are they weak? Alright, so I'm going to give you an example of a weak base. Have you heard about ammonium hydroxide before? Ammonium hydroxide is a weak base. Is that okay? It's a weak base. Now, a salt of ammonium hydroxide could be something like ammonium chloride. A mixture of this ammonium hydroxide and ammonium chloride gives us a type of buffer, which is buffer solution containing a weak base and its highly ionizable salt. That is type 2. Now, what will this buffer contain in excess, in large amount, and in small amount? So at this time, I'm going to do analysis to number 2 type of buffer. Let us find out what it contains in excess, in large amount, and in small amount. Permit me to write this. We are done with type 1. Okay, so the example we are using here is ammonium hydroxide and ammonium chloride. So I'm going to have NH4OH, then plus NH4Cl. This is ammonium hydroxide and ammonium chloride. In the product, what is going to form? Of course, the product will tell us what the solution contains. During ionization, this OH will be given off. Ammonium ion is positive. OH is negative. Here again, there will be a dissociation at this point. Positive, negative. Did you take note of something here? That ammonium ion is contained in each of the substances that forms the buffer, telling us clearly that the solution will contain excess of ammonium what? Ion. Because if we were to write the product, you know that this NH4 will give us 2 moles there. So a buffer solution containing weak acid and its highly ionizable salt will contain excess of the positive ion in that base. A weak base and its what? Highly ionizable salt. It will contain excess of the positive ion in that base. In this case, excess ammonium ion will be contained in the solution of this buffer. What will it now contain in large amount? Let us see what happens here. Are you aware that after this ammonium hydroxide dissociates, this OH negative can be attracted to this NH4 positive in this salt? And of course, if you have NH4 positive plus OH negative, opposite charges, they attract, what is going to happen? What is going to happen? It's going to form back your ammonium hydroxide. But this ammonium hydroxide will be in large amount, not excess. It's going to be in large amount, but not too excess. Because the species formed from something from here and another from here, We're not talking about the chloride ion. We're not interested in that. We're not interested in that. So take note that this solution will contain large amount of what? Ammonium hydroxide. What will it now contain in small amounts? Hydroxyl ion will be in small amounts in this buffer solution. Because you see, it's just only from one of the species that make up the buffer solution. So that is that about type 2 buffer solution. Let us now move on to type 3. A buffer solution that is formed from salt of weak acid and salt of weak base. A good example of that is a buffer solution that contains something like sodium acetate, because that sodium ethanoate or acetate, is a salt that is formed from ethanoic acid, which is a weak acid. Then we have something like ammonium chloride, which is a salt formed from a weak base, say ammonium hydroxide. A mixture of this sodium acetate and ammonium chloride, which is actually a mixture of salt of weak acid and salt of weak base, forms type 3 of buffer solution. And now we're going to do the analysis to see what the solution will contain in excess. So we are here now, type 3. Buffer solution containing a mixture of salt of weak acid and salt of weak base. Permit me to wipe this because we are done analyzing type 2 buffer solution. I gave example in this type 3, sodium acetate mixed with something like ammonium chloride. So let me write CH3, COOH, okay, COONA, sodium acetate, plus ammonium chloride, NH4Cl. Take note that in solution, this will split here. There will be a dissociation here. This is negative, this is positive. The same thing here. Ammonium ion positive, chloride ion negative. Of course, we know that attraction will lead to the formation of something like ammonium acetate. This negative ion will be attracted to this positive ion. The product will be something like this CH3, COO, NH4. Is ammonium acetate. And of course, that substance is what will be in excess. That is what will be in excess. Is that okay? That is what will be in excess. We are not going to talk about the sodium chloride form because that sodium chloride in this case is not the salt that formed this buffer solution. The salt that formed this buffer solution are salt of weak acid and weak base. So we're not considering sodium chloride here that's going to form in the product. Our interest is in the formation of this ammonium acid. So if you have a buffer solution containing a salt of weak acid and salt of weak base, example sodium acetate mixed with ammonium chloride, what is going to be in excess in this case is ammonium acetate. Now we've explained the concept of buffer solution, we've talked about the types. We're now going to establish the formula for calculating the pH of buffer solution, which of course can also help us to obtain the hydrogen ion concentration of a buffer solution.